So today we're actually going to learn to do some of these calculations from the ground up. It's an extremely simple subject. Oh, it said don't cross here, and that's the first thing I did. So let's. All right. So we're going to talk about computing the wave function just perturbatively. And let's start with, let's talk about the approach we're going to take. We're going to use the path integral to calculate the wave function. And let me remind you how we do this even without any time dependence or anything like that. So the path integral, even just say in quantum mechanics, tells us how to go from some phi prime e to the minus IHT phi. And this is a path integral over configurations where phi is locked to be capital phi here, and at some time negative t is locked to be phi prime, e to the I action. And as you're undoubtedly very familiar with, there's a standard way of extracting the vacuum wave function out of this object. So this is an object here defined for finite time, but if I send t, if I send let me say minus t to minus infinity plus I epsilon, then everything here, that there's a piece here that's e to the negative epsilon the Hamiltonian. And so as this, so if I send it to infinity in this way, then everything, if I insert a complete set of states here, everything that's not the vacuum makes exponentially small contributions. And so in this limit, the path integral gives me something that's proportional to psi ground star of phi prime times psi ground of phi. And so this actually gives us two ways to keep track of what the wave function is, but we can just keep track of the dependence on phi and ignore what's going on with phi prime. For example, thank you. So for instance, we can say that we're doing the path integral d phi e to the I s, where phi at 0 is locked to be some phi, and phi, as we go off to minus infinity 1 minus I epsilon in this way, should go to 0, for example. Okay, so if we do that, then this is proportional to the ground state wave function, the vacuum wave function, depending on phi. Okay? Now, typically when this is done in textbooks, we actually go whole hog. We say, let's just do the calculation in Euclidean space. If we do the calculation in Euclidean space, it's just obvious to begin with. It's just in e to the minus ht, and so we're just projecting out the vacuum as we send t to infinity. The reason I'm talking about it directly in this Lorentzian way is that when we're talking about situations in cosmology or with time-dependent background and so on, doing the Wick rotation can be hard, sometimes can be impossible, and so you don't want to rely, I mean, we're breaking the symmetry between space and time, and so we don't want to rely on that in order to do these kind of calculations. So this is really the statement that if we're Lorentzian, but we go off a little bit, this is Feynman's I epsilon. So yet another way of saying this is that we can make sense of the oscillatory phases in this path integral by putting in all the masses or all the frequencies if we put in a damping factor, e to the minus epsilon phi squared in the path integral, and so we'll see that momentarily. We'll see how that's equivalent to this. But this is really the same as Feynman's I epsilon. Okay, so let's actually start with the harmonic oscillator then. So let's start with the calculation of the wave function for the harmonic oscillator in this way. Again, presumably many of you have seen this calculation. So so the action is integral. I'm always going to call my time to be eta. Phi dot squared minus a half omega squared phi squared. And so we want to do the path integral, d phi e to the I s, with these boundary conditions, where phi at 0 is some phi, and phi at and phi at minus infinity plus I infinity goes to 0, plus I epsilon infinity goes to 0. Okay, well, how do we do this calculation? Well, this is a Gaussian integral. So for Gaussian integrals, we know that the path integral for a Gaussian, so because Gaussian, this is just proportional to it's e to the I, the action evaluated on the saddle point, the classical solution. But the classical solution has to, of course, satisfy these boundary conditions. So what is the most general classical solution that I could have? The most general classical solution I could have to the equations of motion. So my equations of motion are phi classical double dot plus omega squared phi classical equals 0. My most general solutions are phi classical is a e to the I omega eta plus b e to the minus I omega eta. Okay? But immediately, I see that I have to have b equals 0. Okay? I have to have b equals 0 because if b is non-zero, as I go off to minus infinity plus I epsilon infinity, this thing would blow up like e to the epsilon infinity. Okay? So b has got to equal 0. I'm left with a, and so now I have to impose a boundary condition that phi of 0 is equal to phi. So my classical solution is just equal to phi e to the I omega eta. And here we can see the same comment I made a moment ago, that we can also see that this is the solution I need to keep if I imagine that I went back here and I regulated the action by putting a plus I epsilon phi squared here. Okay, so we know that if we do that with the e to the I in front of the action, that I get a Gaussian suppression and everything is fine. So that means that if I shift omega to omega minus I times something imaginary, then everything should be damped as I go off to minus infinity, and that's exactly what this solution does, whereas that one would blow up. Okay? So this is a very important point we're going to see over and over again, but the physics of being in the vacuum, in the deep past, which is what we're doing when we're trying to compute the vacuum wave function, okay, that physics is encoded in the behavior of these solutions as we go off to minus infinity, and they always have to have positive frequency modes, no negative frequencies as we go off to minus infinity. Okay, is that clear? Any questions about that? Again, feel free to interrupt at any point. Yes? Yes? Oh, great. I'm coming to this and just thank you. That's that was the next thing I was going to talk about. So this, now, does it bother you? Just the questions meant to ask? This classical solution is complex. The field is real. The classical solution is complex. Okay. Does that bother you? It shouldn't bother you because this is true of every Gaussian integral, even the classic standard Gaussian integral. So let's talk about this for a moment. So let's say we are doing the integral minus infinity to infinity e to the minus ax squared plus ibx. Okay? Let's say we want to do this integral. Now, this is supposed to equal the action, in this case just that function evaluated at the saddle point. But where is the saddle point here? The saddle point is when, so let me put a z. Z. Okay. So the saddle point is at z equals b over 2a. I, b over 2a. Okay? So the saddle is also not on the contour of integration. And that's perfectly fine. In fact, the saddle is not a contour of integration. This is also a horribly oscillatory integral because of the phase, right? So the saddle point is here at IB over 2a. The integral is running from minus infinity to infinity, but because it's vanishing suitably at infinity here, I can, by contour deformation, I can say that this integral is equal to this integral. Now, on this path, and for something as simple as this, if I literally just make it a parallel line to this one that passes through there, you can very easily check that now on this contour, the exponent is purely real and negative, right? So there's no oscillations there at all, and so the saddle point approximation, first is a Gaussian integral, so the saddle point approximation is exact, but also it's also a sensible thing to do because there aren't any phases, okay? So this is a typical fact of life about Gaussian integrals. When you evaluate a Gaussian integral by evaluating on a saddle point, very often the saddle point will not be on the contour of integration, and you shouldn't freak out. That's totally fine. Now, that's great for Gaussian integrals. Of course, it's great anywhere in the neighborhood of perturbation theory. When you extend this to looking for things like wormhole solutions in quantum gravity or things like that, it gets very confusing because we don't understand. They're very high-dimensional integrals. It's not obvious if there is contour deformations that do what you want. It's not obvious that every saddle point should contribute or how, and so on. But for things like this, everything is perfectly fine and under control. Does that answer your question as well, Spenta? Well, I think Spenta asked the question so I would remember to answer it, so thank you. It was in my notes, though. So it was all right. So okay. So, but now let's actually compute the action, and we could do it just by shoving this thing in and just shoving it in and doing the calculation. But again, I want to do things in a way that will slightly generalize. So, in order to actually compute S of phi classical, I'll just begin with the again very familiar observation that this thing I can write as a half d eta of phi dot phi minus phi times phi double dot plus omega squared phi. Okay, so I hope that's clear. And so therefore, the integral of this is equal to the integral of that. This is the equation of motion. So this piece is 0, but I'm now evaluating it on the classical solution. Okay. If I evaluate this on the classical solution, this piece is 0. So I'm just left with this, and this is purely a boundary term, and it only has a contribution, again, because everything is vanishing as we go off to minus infinity, it only has a boundary contribution at eta equals 0. And so this, in the end, is just a half by classical dot at 0 by classical at 0. And so what is this with our solution for phi classical? This is I omega phi squared over 2. Okay? And therefore, psi of phi equals e to the I action evaluated on phi classical is equal to e to the I times I half omega phi squared is our friend e to the minus a half omega phi squared, the ground state wave function of our harmonic oscillator. Okay? Any questions about that? Sorry? No, well, I mean, here what I wrote it. I mean, I'm reserving phi for the boundary value, phi of 0, okay? if you don't see an of eta explicitly, it's always some boundary quantity. Okay, great. So that's the ground state wave function of the harmonic oscillator. What about the ground state wave function for a free field in quantum field theory? Well, it's exactly the same thing. So psi of phi now in a free field, free scalar in QFT. Well, this is just a whole bunch of harmonic oscillators, so I can write it e to the minus a half omega k, omega for the kth mode, and then there's going to be a phi of k, and then the phi for minus k. Now, I've written it in this way, so it's implicit that I'm summing over all k. So summing over all k is really an integral over k. So if I want it to be more, pedantic, I would write this would really be some integral d minus 1k omega k phi of k phi of minus k. And if phi is a real field, as I'm assuming, the Fourier mode phi of negative k is the complex conjugate of the Fourier mode of phi k. So this is also equal to integral dd minus 1k omega k phi k mod squared. So again, manifestly positive. It's a damped ground state wave function. All right. So that's what the ground state wave function of a free scalar in quantum field theory looks like. Now, we don't normally, especially in high energy physics, at least in most of the sort of standard textbooks and so on, we don't spend a long time talking about the vacuum wave function. It's a vacuum wave functional. So if you give me some phi of x, psi of phi gives you psi phi mod squared would give you the probability that you would measure that phi of x in the vacuum. Okay? Sorry? I'm not worried about the prefactor. I'm just worried about the dependence on phi. And the reason is I'm ultimately interested in calculating expectation values, and so all the prefactors will cancel out when I do that. Okay. Okay, but let's just get a little bit of intuition for it. So let's say I want to know what is the wave function. It's a wave functional, but what is a wave functional for a configuration of phi that kind of is in a sphere of radius r, inside is phi naught, outside is phi equals 0, say. Okay? So what is that? Well, we don't really have to do any formal calculations. It's clear that what I'm going to get is something, it's Gaussian, so it goes like e to the minus phi naught squared. And the fact that there's one power of k there, so just very, very naively, there's a k here, right? There's so just the dimensional analysis gives you a power here of r to the d minus 2, and you can get that sort of formally by shoving it in. Okay, now so that tells you in particular that the sort of typical size of the fluctuation of phi in a sort of sphere of radius r is of order 1 over r to the d minus 2 over 2. Now, of course, you recognize d minus 2 over 2 is the engineering dimension of phi, right? That's, but here you see a little bit more, perhaps just slightly more vividly what that engineering dimension means. Okay, it means that it tells you the sort of typical size of the fluctuation for the scalar field to imagine. And notice the famous big difference between d equals 1, d equals 2, and d bigger than 2, space-time dimensions. D equals 1 space-time dimension, this fluctuation gets bigger and bigger as r gets larger and larger, right? So delta phi is going like square root of the size of the box. Why do you know that? That's simply the fact that the ground state wave function for a particle in a box is completely delocalized across the whole box. Okay? Now, next, in d equals 2, this seems to not depend on anything here. Of course, we know all these powers really turn into logarithms. And so there's the fluctuations in phi grow logarithmically as you go to larger and larger distance. In d equals 3 and above, the fluctuations get smaller as you go to larger and larger distance. Now, what is this the effect of? Why is there this difference? How is quantum field theory different than quantum mechanics? Okay? If you imagine you took a field and you just put it on the lattice everywhere, you just have a whole bunch of different individual particles on each site, quantum mechanics particles on each site, except for the gradient terms. If you shut off all the gradient terms, then you would just have an individual quantum mechanics on each site, and there would be humongous fluctuations. But it's the gradients which suppress the fluctuations. Okay, so we see that starting in 2 dimensions, 3 dimensions and higher, the gradients are strong enough to suppress the fluctuations on all scales. This is why the notion, for example, of a vacuum expectation value makes sense in d bigger than 2, but not in d equals 2 or d equals 1. Okay, because it doesn't even make sense to talk about what I mean by the value of the field on very large scales. It fluctuates too much. Okay, now this you're probably all very familiar with. Let me give you just another example, just to show you how thinking about the vacuum wave function can help your intuition. Many of you probably know that in the standard model of with the Higgs mass at around 125 GeV, the quartic coupling that goes along with that is so small that when you run to high energies, the quartic coupling goes negative, and people talk about a vacuum instability associated with the Higgs in the standard model. Okay? So let me give just a quick discussion of that. Let me take an extreme case. Suppose I gave you a potential that looks like minus lambda phi to the 4. Minus lambda phi to the 4. Okay? What do you think what's your first instinct when you look at a picture like that? So you have that and that, we want to be stuck up here near phi equals 0. Well, it looks very scary, right? It looks like it's just its potential, totally unbounded below. And then if I asked you, so what's the lifetime of the vacuum? What would your gut instinct be? Your gut instinct might be instantaneous. I don't know. I mean, it's just going to go somehow, right? It just looks terrible. But in fact, if you just spend one more second thinking about it, you'd say, well, let's see, when I do any calculation in perturbation theory, do I see any hint of the sort of imaginary part for every quantity that would have to be there if the vacuum was unstable? No, you do not. Okay, so to every order in perturbation theory, it looks like the vacuum is stable. So what the heck is going on? Well, what's going on is, what does it actually take in order to go down here? Your mental picture that you're just going to slide down is if this was a particle. For that to apply to the VEV in the whole universe, you'd have to have everywhere in the universe phi fluctuate down, and that's ridiculously unlikely. Okay, so let's in fact get an idea of what we need. I need to have some fluctuation of phi in order to go down that. If I have some phi naught here in a circle of radius r, there's a potential energy that I would gain, lambda phi naught to the 4th r cubed, but it has to compete against a gradient energy, right, from the fact that phi is changing. So this has to be comparable to the gradient energy that would be, it's a gradient, so it's phi naught over r squared times r cubed again. And so this tells me that the typical fluctuation size, the typical phi naught I need in order to make a bubble that then would want to grow to swallow everything up would have to be of order 1 over r squared, 1 over lambda. Okay? And therefore, how likely is it for that to happen? Well, the wave function tells us, right? So the wave function for what we could call the death bubble actually goes like e to the minus 1 over lambda. Okay, so it indeed is not something that we see in any order of perturbation theory. Now, if I told you, so here it kind of makes sense because lambda was dimensionless and there's nothing to set a scale. Okay, there's nothing to set a scale for the instability rate. Now, what if I gave you something like a phi cubed theory, mu phi cubed? Now there's a scale there, right? Let's actually go further. Let's say I give you a tachyon. So something just sitting there, m squared phi squared, but with a minus sign, minus m squared phi squared. Then you say, well, the time scale for the instability is m. Or if I give you mu phi cubed, you say the time scale for the instability is mu, right? But that's actually not in contradiction at all here. It's not in contradiction with the fact that we don't see anything in perturbation theory. You see, in those examples, the couplings are relevant operators. And so the dimensionless strength of the coupling is growing as you go to large distances. So you make the bubble bigger and bigger, the size of the coupling is growing, and at a big bubble, it's completely, the strength is of order 1, and there's no suppression at all. Okay? And in fact, if, let's say, you took a phi cube theory, but you put it in a pretty small box, whose size was much smaller than the scale set by 1 over mu, again, you would not let the coupling get big, and again, you would find that the instability is exponentially small. Okay, so all this vacuum instability stuff is always exponentially tiny in the coupling constant. Perturbation theory is very smart. Okay, perturbation theory says nothing is happening in perturbation theory, and everything has got to be some exponentially tiny effect. All right. Okay, so those are just a couple of examples of how it's useful to have this intuition about what the vacuum wave function looks like. And of course, all the excitement about thinking about the structure of entanglement in quantum mechanical systems and field theory has refocused the attention of a lot of high energy physicists on thinking about vacuum wave function. But even for less fancy things, it's a useful thing to try and build some intuition for. Professor Sen. Yes, it does make a difference. So in a little bit more detail, the actual instability rate that you would get would be given by the size of the, let's say we're in 4 dimensions, would be given by the size of the bubble, 1 over r to the 4th, e to the minus 1 over lambda. Okay, and so in fact, so there was some even dependence on r here, and we would have to integrate over bubbles of all sizes because this thing doesn't classically doesn't depend on it. But as you say, quantum mechanically it does, and so in fact, the one loop correction and the determinant out in front effectively just does that. Okay, so you get 1 over r to the 4th, e to the minus 1 over lambda, 1 over r. In the standard model, there's a little peculiarity that this whole combination is such that the entire instability rate gets around equal contributions over around 4 decades of running. So it's quite strange. And that's why people actually do, you want to get a reasonably accurate estimate, you really have to go to 2 loops. So, yes, but that's the one loop improved version of the computation. Okay. Anyway, so you should play around with this a little more. But now let's go on. Yeah. Yeah, this is 4 decades. Between around 10 to the 11 and 10 to the 15 GeV. The actual coupling constant turns negative at around 10 to the 10. And so over a pretty big range, you get comparable size contributions. And so people actually have to do a 2-loop calculation to get a pretty reasonable estimate. All right. Now, this was all for normal time-independent problems. Let's now move on to time-dependent problems. And so I'm going to do exactly the same thing, except now we'll do a general time-dependent harmonic oscillator. So now we're going to move on. So now my action is going to be the integral of a half a of eta phi dot squared minus a half b of eta phi squared. Okay? For the saddle point, we still want to solve the classical equation of motion. So the classical equation of motion is a phi classical dot plus b phi classical equals 0. And we're always going to be interested, just like we were before, and we're always going to be in a situation, and all the things that we care about, that as eta goes to minus infinity, there's going to be a solution which is essentially oscillating. It'll go like e to the I eta or e to the minus I eta, and we're always interested by the same logic as before, because we want to make sure that we started adiabatically in the vacuum in the past, despite the fact that it's time dependent. We want to look for a solution. So I'm going to say that there are solutions f plus minus of this equation of motion, but I'm interested in keeping the solution f plus of eta that goes to e to the I something positive eta as eta goes to minus infinity. And then for the saddle point that matters, our solution phi classical of eta is going to be phi f plus of eta divided by f plus at 0. Sometimes I'll call 0 eta naught because we might later want to be a little careful about regulating it. Okay, now let's now compute the classical action. So S classical. So now again, a half A phi dot squared minus a half B phi squared is equal to a half d eta of A phi dot minus a half phi times d eta A phi dot plus B phi. So it's exactly the same story. This is the equation of motion. So it'll integrate to 0 just by its value at eta naught. Okay, so all I'm doing f plus at eta naught. Okay, so that's just designed to make it match for this to be 1. That's right, exactly. F minus, that's right. F minus is going to look like that. Okay, and so finally then, e to the I s of phi classical, is then equal to e to the I a at 0, so I'll call that a naught. F dot of 0, f of 0 over f of 0 squared times phi squared over 2. So it's actually convenient to write this as e to the I over 2 a naught. And you see, this is just dd eta of log f. F plus, all f plus, evaluated at eta naught times phi squared. Okay, so this is psi of phi. Now it'll be, what's going to happen is in all of our calculations, we're going to find that what happened for the harmonic oscillator was that psi of phi was manifestly real. In all of our calculations, we're going to find that psi of phi actually has some phases in it, but we don't care about the phases for doing any of the expectation value calculations because they go away in psi mod squared. So let's just compute psi mod squared right now as well. That'll make our life easier in the future. So psi mod squared is then just equal to e to the minus phi squared, the imaginary part of a naught d eta log f plus. Okay, evaluated at eta naught. Okay, so in the particular case where we go back to the harmonic oscillator, f plus was e to the I omega, and so the imaginary part is just of d eta log f is just omega, and that's indeed what the psi mod squared is. Okay, so any questions about that? All right, while we're at it here, let's also, once and for all, compute what the Green's function is, what the propagator is associated with this time-dependent problem. This is, of course, going to come in handy. So let's compute the Green's function. In other words, all we want to do is invert the quadratic part of the action. It's just quadratic by itself, of course. The quadratic operator. So let's just do it. So we're looking at d eta of a g of eta and eta prime plus b eta, plus bg of eta and eta prime is delta of eta minus eta prime. Okay, so that's what we want to solve. And as usual, even from your childhood quantum mechanics, whenever we have problems like this with then here I'm imagining this is eta, here is eta prime, and so up here I'm going to have some solution of the, up here I'm going to have one of the classical solutions, down here I'm going to have one of the classical solutions, and I just have to match the jump conditions. I could just write down the answer immediately. The answer is a time-ordered product, blah, blah, blah. I could just declare it, but I just want to spend 1 second just so you see, even in these time-dependent settings and so on, how these simple things, standard things arise. So up here, I won't call the solutions F plus and F minus because those mean something. So let me call the solution here F1, whatever it is. There's a solution F1, and then I'm going to say that it has a coefficient, which of course might depend on eta prime. And down here I have F2 and some capital F2 as a solution as a function of eta. And now I have to match. So I have to make sure that the function is continuous. So that says that F1 is equal to F2, F2. But also if I integrate this equation across eta prime, I'm going to get 1 on the right-hand side. On the left-hand side, I'm going to get a jump condition on that guy. Right? So the jump condition on him is that A F1 dot, A little F1 dot, minus A little F2 dot is equal to 1. Okay, so these are now just 2 equations and 2 unknowns that I can solve for little f1 and little f2. And so what I find is that little f2, 1, is equal to the f of the other guy, as you'd expect, is f1, 2, eta, of eta, divided by a f1 dot f2 minus a f2 dot f1. Okay, so that's literally what you get just by solving those 2 equations and 2 unknowns. Sorry? Yes, this is all at the eta. This is all at the eta. This is all at eta. This is all at the eta prime. Okay. This is all at the jump. Okay. Yes. Oh, I'm sorry. That's because I forgot to put the d eta. That was part of the equation of motion. Sorry about that. Thank you. Okay. Now, actually, this is a famous object downstairs. Okay. So whenever you see in all the books doing, field theory and curved space and so on, there's always this business about normalizing the solutions with a phi 1, d, forwards, backwards, phi 2. This was known to someone called Mr. Wronski. I could be wrong, but maybe his name was actually Wronskian, although that would be kind of weird. But anyway, it's also the Wronskian. Whenever you have a second-order differential equation, that object is very nice for a simple reason. Let me do it over here. That it's trivial to see that d eta of a f1 dot f2 minus a f2 dot f1 is actually equal to 0. Okay. Just because by the equation of motion, d eta of a f1 dot is equal to bf1, that's equal to bf2, and they cancel each other. Okay, and so it's because it's a constant, it's reasonable to normalize it to be something. Okay. Now, in fact, it's reasonable to normalize it to be af1 dot f2 minus f2 dot f1. It's reasonable to normalize this to be I. If you think about what it is for the harmonic oscillator, it would have just been it would be imaginary. And another way of motivating it is that there's an operator dt here. Well, it's naturally anti-Hermitian. So if I multiply minus I dt, then that's something that's reasonably real on the right-hand side. In any case, that's just a normalization choice. And with that normalization choice, we finally have the formula for the Green's function, that g of eta and eta prime is equal to, when eta is bigger than eta prime, it's one thing, it's f1 of eta, f2 of eta prime, and I guess I should put a minus I here. Or an I here. Okay? So that's the familiar kind of thing you've always seen. For the Feynman propagator, it's a time-ordered product, but now we are seeing it at just totally general time-dependent setting. Now, of course, I haven't told you what F1 and F2 are, and this problem by itself doesn't uniquely fix the Green's function. I can always add a solution of the homogeneous equations. Here I see that by the freedom that if I take F1 and 2 and I shift it to F1 and 2 plus the same thing, plus x for both of them, x of eta, let's say, the Wronskian does not change, nothing changes, so I can freely shift by any solution of the free equations of motion. Okay? So what Green's function you choose depends on the boundary conditions that fix that freedom. Now, let me talk about, even though we're not there yet, but since we're in this neighborhood, we can just finish it. It's very easy to motivate a set of boundary conditions that we care about for our problem. Because we're doing the path integral with fixed boundary conditions in the future, after we shift around some classical solution like we've done here, the fluctuations around that should vanish at the boundary. So it's very reasonable to demand two things. So our boundary conditions for the Green's function are, one, that, again, as usual, as either eta, let's say as eta goes to minus infinity, 1 minus I epsilon, okay? Then this thing should go to 0, okay? So that's the past boundary condition, because we don't want the fluctuations to ruin that. And 2, we want that g, as either eta goes to 0, or eta prime goes to 0, either one, that we want this to also go to 0. Okay, so again, this is vacuum in the past, and this is the fact that we're computing the wave function rather than a scattering amplitude or something else. So we want fixed boundary conditions at eta equals 0. Okay, and that now tells us, in terms of f plus and f minus, what our Green's functions are. Property 1 tells me that that whichever time is earlier, I can only have f plus in front of it. And then property 2 will fix the homogeneous part. So the Green's function that we get of relevance for our problem is when eta is bigger than eta prime. So eta, so when eta is the early time, I should have f plus of eta and f minus of eta prime plus the other way around. And whoever's earlier, it should have the f plus associated with it. So in this case, eta prime is earlier. That's f plus of eta prime, f minus of eta. But let's say eta prime goes to 0. Okay, If eta prime goes to 0, then this thing is going like f. As eta prime goes 0, this is going to f plus of 0, f minus of eta. Right? That's not 0. So I have to add something to cancel the behavior at 0. And what I have to add is the solution of the homogeneous equation, which is just f minus over f plus at 0 times f plus of eta, f plus of eta prime. And that's what I have to add in order to cancel the behavior, in order to cancel g near eta equals 0, while not messing up the fact that it has the right positive frequencies as I go back to minus infinity. Okay? Is that clear? Any questions? So let's write this down, for example, for the case of the harmonic oscillator. So for the harmonic oscillator, first let's see what is our f plus minus was just some normalization, e to the I omega eta plus minus omega eta. So our Wronskian was f plus dot f minus minus f minus dot f plus, which is 2 I n squared omega, and therefore n is this famous 1 over root 2 omega that we all know and love. And so the Green's function, see, we didn't have to worry about do any of this normalization stuff for the calculation of the wave function. We didn't do it, but we need it here for the Green's function. And so the Green's function, in this case, g of eta and eta prime, is theta, eta prime minus eta. Yeah. Yes, that's right. The same as normalization by norm in the Fock space, all that stuff. But I'm precisely not using that language. I'm just, I mean, yeah, of course. That's right. That's right. That's right. Yeah, I mean, of course, these are Gaussian problems, so we can solve them every which way. I'm doing it this way just to have one uniform attitude towards everything, which we can. Okay, so that's it. That's everything that we need to know about time-dependent problems. And then from here on in, it's just applications of these simple formulas, at least for Gaussians. So let me just stop here again, ask any questions. Everything totally clear? I suspect this is very familiar to most of you. So, okay. So let's now apply this to calculating the vacuum wave function in de Sitter space, and all the things that I was saying just with hand waving yesterday. Let's see properly. So the rest of the lecture, we're going to just calculate the next little bit. We're just going to compute what the vacuum wave function looks like for particles of various masses in de Sitter space. Okay, so first let's put it in the form of our general time-dependent problem. So the metric in de Sitter. So now we're going to do ds4 just for concreteness. It doesn't really matter. But so the action is d4x root g. The action for a scalar field is half g mu nu, d mu phi, d nu phi, minus a half m squared phi squared. The metric is dt squared minus e to the 2ht dx squared. And as usual, I'll introduce conformal coordinates, eta, to write this as 1 over eta squared times d eta squared minus dx squared, where eta is related to t as negative e to the t, negative e to the negative t. Okay? And I'm now working in units, just to save myself the grief. I'm working in units where the Hubble constant is set to 1. Okay, so we have the usual picture that that time goes to minus infinity is eta goes to minus infinity. Time goes to plus infinity is eta goes to 0. Okay, so we have this picture of eta, then everything is going to be computed. All the correlations we're interested in are computed at the surface eta equals 0. Okay, so let's look at what the action is. So the action is integral d eta d cubed x. So root g is just 1 over eta to the 4th. And now g upper mu nu is an eta squared of eta squared phi dot squared minus grad phi squared. Then I have minus m squared phi squared. And now let's immediately go to momentum space. So I won't bother writing an integral again. I'll use the same notation we had before. So this is going to be 1 over eta squared, a half phi dot squared, now for some k, minus a half k squared, phi k squared, and then minus a half m squared over eta to the 4th, phi k squared. All right, so relative to our general problem, this is a of eta equals 1 over eta squared, and b of eta is equal to 1 over eta squared times k squared plus m squared over eta squared. Okay? All right, so after this, now it's just all application. But first, let's see what the classical equation of motion is. Logan, you seem unhappy. Okay. All right, so the equation of motion is just d eta of 1 over eta squared phi dot plus 1 over eta squared k squared plus m squared over eta squared phi equals 0. I can write this in various ways. Here's, just write it out most naively. So it's just phi double dot minus 2 over eta phi dot plus k squared plus m squared over eta squared phi equals 0. And so we see the general phenomenon that we talked about as eta goes off to minus infinity. This term drops, that term stops, and I just have phi double dot plus k squared phi equals 0. And that's just the physics of these are k is a co-moving k. So as I'm going off to eta equals infinity, the physical wavelength is getting much smaller than the curvature scale of de Sitter space, and therefore that's just flat space. Okay, so that's the flat space limit. But of course, as eta gets small enough, eventually this term dominates over that. And that's the dynamics of Hubble friction, and all the rest of it has to do with that. But But actually, for our purposes, really, it's just important to point out that we are matching flat space physics as eta goes to minus infinity. Now, before solving this equation in general, let's look at some special cases for some intuition. So one special case is just m squared equals 0. So there's two special cases, or two nice cases. So one is m squared equals 0. And when m squared equals 0, I'll leave this as a small exercise for you to show that there are two solutions. Okay. That's a little exercise to show that these solve the equation of motion. Very simple exercise, but let's see how with this solution we can find the vacuum wave function. Okay, so the one we want is the plus sign, so f plus is equal to e to the I k eta 1 minus I k eta. So remember, we want to do log f plus. So log f plus is log 1 minus I k eta plus I k eta. And I'm supposed to look at the imaginary part of a d eta log f plus evaluated eta naught. Okay, that's the object. This is the object that goes in the vacuum wave function. So before I take the imaginary part, if I just look at d eta log f plus, okay, well this is minus ik over 1 minus ik eta plus ik, just from the d eta. And so you see that well, as eta goes to 0, so now as eta goes to 0, this goes to k squared eta plus I k cubed eta squared plus dot dot dot. Okay, so that's what it looks like as eta goes to 0. So let me put an eta naught here. So that's as eta naught goes to 0. So you see there's this dominant piece that looks like k squared eta naught in the wave function. However, it's a phase. Okay, so it drops out when you take the psi mod squared. Okay, so there's a dominant piece that goes like that, but it drops out when you take the psi mod squared. The imaginary part is dominated by this first term here, right? And therefore, the imaginary part of a d eta log f is equal to, remember, a is 1 over eta naught squared. And from here, I have k cubed eta naught squared. So the eta naught squareds nicely cancel, and I'm just left with k cubed. Therefore, psi of phi mod squared is equal to e to the minus phi squared k cubed. And if I restored the dependence on Hubble just by units, there would be a 1 over Hubble squared. Okay. So this is how we can see that, for example, the two-point function in momentum space, k1, 5, k2, is equal to h squared over k cubed delta of k1 plus k2. And it's how I can see that in position space, 5x, 5y is h squared log x minus y, again with some IR cutoff here. Okay, let me just take, since I'm out of time, but let me just do one more example quickly. And that's the case where m squared is equal to 2. So when f squared equals 2, this actually corresponds to the conformally coupled scalar. You can completely get rid of all the time dependence on the problem just by doing a simple transformation. Phi goes to eta phi. But you can also discover that just by solving the equation of motion. And in this case, you find that the solutions are, the classical solutions are eta e to the plus minus I k eta. Okay. So just up to the eta factor, it's just these fields. Once again, the solution we want is f plus is eta e to the I k eta. And so d eta log f plus, the imaginary part of d eta log f plus is just equal to ik, is just equal to k. And therefore we have that psi of phi mod squared is equal to e to the minus k, just the magnitude of k, phi squared. And then there is the factor of, the overall factor of a, which is over eta naught squared. Now, does this bother you? We have this funny dependence on eta naught. I thought we were setting eta naught to 0, right? So there seems to be some explicit dependence on eta naught here, right? Well, let's look at what the actual 2-point function is. And again, anyone who's done computations in the ADS is saying exactly the same phenomenon. In fact, just to make an obvious point while I'm erasing, because of the symmetries, the solutions, everything, all these things are simple analytic continuations, or sometimes identical to, in these cases, what you get in the ADS. The real novelty and difference between de Sitter and ADS, even at this free field level, occurs when you have massive particles that are much more massive than Hubble, for a reason that we'll see in a little bit. But all these cases are very similar to things that you see in the ADS. In any case, if you're not familiar with the ADS calculations, what would we get here? So here, if I look, for instance, at the 2-point function in space, the e to the minus k phi squared is what we always get in a free theory. It should be, right? Because it's just conformally related to a free theory. So I would get 1 over x minus y squared, except now there's some eta naught squared overall out in front. And that's exactly correct, because the x's are also co-moving coordinates, and the eta naught is precisely there to convert this to the physical distance between the particles. So this is really the actual distance between x and y squared. Okay? So there's nothing mysterious about the presence of the eta naughts. They're there essentially by dimensional analysis to make sure that the co-moving coordinates that we're using are turned into actual physical distances. Okay? Now, my time is up, right? I have 20 more minutes. Oh my goodness. Thank goodness. You know what happened. That's what you get when you don't change your clock, your watch. So, all right. Yeah, nothing made sense. That was like an hour and a half ahead. All right, great. I have 20 more minutes. You shouldn't have told me that. Now I'm much more relaxed. So, okay. Yeah, me too. Okay, so now let's work out the general case. So we've written down the equation of motion. Let me write it. Of course, the usual way, I could just stop at this point and say this is a Bessel function and blah blah. Okay, I want to tell you a little bit more. So let me multiply by eta squared. Okay, so this is one way of writing our equation of motion. Now, note that there are things that look like eta dd eta, right? These are sort of dimensionless derivatives. So let's introduce that sort of dilation derivative, which, by the way, is nothing other than the old time derivative in terms of the old time coordinates. Okay, but let me just leave it as, let me call it d. Right, well, I mean, a simple observation is that d squared is, of course, just eta squared dd eta squared plus d. Okay, when the piece that the derivative hits the eta and the dd eta, and therefore I can rewrite this equation as d squared minus 3d plus k squared eta squared plus m squared phi equals 0. And so this, of course, begging you to complete the square. So this is d minus 3/2 squared plus k squared eta squared plus m squared minus 9/4 phi equals 0. Okay, because of the minus 3/2 there, it's very reasonable to just factor out of phi a piece that goes like eta to the 3/2. Okay? So let me do that. Let me say that phi is negative eta. Remember, eta is negative, so we'll always see negative eta as a positive number. Negative eta to the 3/2 times chi. And if I say that it's chi that only depends on the quantity minus k eta, so if I call this object d eta, remind me, then the equation for chi is the Bessel equation. Chi is equal to 0, or I've defined nu squared to be 9/4 minus m squared, which I'll also often define to be negative some mu squared. Okay, so it's some mass that's affected by something of order Hubble. Okay, so this is the Bessel equation. Right? And now I just want to say a few words about Bessel functions. There are general things about all the famous special functions of physics that were solved in the 1800s. And I'm saying this only because I sometimes see in papers, a lot of physics papers look like you set up some equation, you get a special function, then, of course, you're interested in this limit, that limit, and you say, then we pull out the following known limit properties of Bessel functions, or Hankel functions, or hypergeometric functions, or whatever, right? And that's, of course, perfectly fine. It's correct. But it's also cheating, because that's where all the action is. All the cool stuff is happening because you know what those limits look like. So at the very least, you should have /cite, Euler or Gauss, or the people who actually figured out what all these things look like. Okay, so I actually want to just say a tiny bit about what the sort of drama of Bessel functions is, because it's actually directly relevant for the questions that we're going to be thinking about. See, the whole reason the story of Bessel functions is interesting is that this differential equation has a tension between two symmetries. Okay? As z goes to 0, so as z goes to 0, this equation looks like dz squared minus nu squared chi is equal to 0. And so it has a scale invariance, right? It has a scale symmetry. And in fact, there are natural solutions here that exhibit the scale symmetry, which go like z to the plus or minus nu. Those are the things that solve dz squared minus nu squared equals 0. On the other hand, as z goes to infinity, the nu doesn't matter. Remember, there was the z squared dz squared in front of that. The equation becomes dz squared plus 1 chi equals 0. Now I have a translational symmetry. And my solutions look like e to the plus or minus iz. Okay? The whole problem has neither scale symmetry nor translational symmetry, but as z goes to 0, it has a scale symmetry, and therefore there are solutions that behave nicely under that approximate scale symmetry near the origin. As z goes to infinity, it has translational symmetry, and it has solutions that are nice under that translational symmetry that are the plane waves. So it's reasonable to give names. It's a second-order differential equation, has two solutions. Okay, so it's reasonable to give names to the solutions that behave nicely under the two symmetries. The name for the solutions that behave nicely in the z goes to 0 limit is Bessel. The name for the ones that behave nicely in the z goes to infinity limit is Hankel. Okay, so Bessel functions are j plus minus nu of z, and they're the things that look like z to the plus minus nu as z goes to 0. Then there's Hankel, and here for historical reasons that I will not mess with, instead of calling it plus minus, they have 1 and 2, so we have Hankel 1 nu of z, which goes like e to the iz, and we have Hankel nu 2 of z that goes like e to the minus iz. Okay? Now, if all you knew was about differential equations, if your only intuition was about, thinking about differential equations as telling you what happens next given what you know now, right? So you integrate gradually, okay? Very local picture of what a differential equation is telling you about. Okay, this is very nice that there are two kinds of solutions, but now there's a natural question. Let's say I give you the solution, which is like one of these guys, which is nice around, which is nice under dilations around the origin. Which combination of the two solutions that are nice under translations is it at infinity? Or vice versa, okay? So you'd like to know what is the relationship between these two sets of solutions. Any one can be written as a linear combination of the other two. And this is the reason why those guys in the 1800s accomplished something when they played with these special functions. I mean, you might wonder, whenever you run into some complicated differential equation, why not just give it a name, right? And then it'll be your famous differential equation, and that's it, right? What's the big deal? After all, these are complicated functions. They're not like or hypergeometric functions or any of these things. And the point isn't that they're just random differential equations that you give names to. These were very practical people back in the mid-1800s, and they actually wanted to be able to compute them, and they wanted to have the answers to all these questions. Okay? So what's really non-trivial is that these interesting differential equations that they studied to death in the mid-1800s have an amazing property, which is not sort of so super obvious when you just think about them in terms of in this differential local way. They have the property that you can say global things about them. Okay, that we can answer this question: how does this guy that's well behaved at the origin transform into the sum of the things on the other side? Okay? And then when we go to the generalization of the mother of all these things, which are the hypergeometric functions, they have monogamy properties, they have lots of interesting properties again, but it's all about relating the solutions with well-behaved, with the standard behavior in the neighborhood of the singularities. And the reason this can happen is something slightly miraculous, which is that not only do these functions satisfy differential equations, they also have integral representations. Okay? And so, for instance, for Bessel functions, there's an integral representation that looks like this. Integral dt, e to the z sinh t minus nu t. And I'm deliberately not giving you a contour. I'm not telling you where to integrate it. The non-trivial point is, and this is something that you can just play with yourself if you've never done it. These are the kinds of things that Euler discovered, is that these integrands have the beautiful property that when you act on them with the Bessel differential equation, the Bessel differential operator on the left on Z, thought of as kind of external data of this problem, then what you're left with is a total derivative in T. Okay? Now, in all the cases where this is certainly shown in textbooks, this is a little bit of cleverness. There should never be cleverness in anything, right? There should be deeper reasons. Of course, now we know there are deeper reasons for these things. But in any case, here you can easily just play and be clever like Euler and discover that the Bessel differential operator actually turns it into a total derivative. Because of that, no matter what contour you do this integral on, you're going to get some solution to this differential equation. Okay? And now what you can do is choose the contours appropriately in order for them to give you the limits that you're interested in, and then use contour deformation arguments to then tell you how one solution can be expressed in terms of the other one. So for instance, you can use this and find the correct contour to turn it into Bessel, and then you do a stationary phase approximation on that object, now at very large Z. You see, the whole picture of Bessel is tied to the origin. And you can give a series expansion for the Bessel function in the neighborhood of the origin, no problem. But if you want to know what it looks like at huge Z, you can't sum that series. That series is a finite radius of conversion. You can't just sum the series trivially. So you need these integrals give you a way of continuing getting the answer anywhere. And you can do a stationary phase approximation to them and see it decomposed into the sum of pieces with the different frequencies that then tells you what linear combination of these guys show up. All right, so that's just my small comment about special functions, but there's something interesting going on. This local global connection is a property of all the special functions that we see in physics, and is something rather remarkable. It's not sort of super obvious ahead of time that things like that had to happen. Okay, but in any case, you can work it out just literally in the way I said. You take the integral representation of the Bessel function, you take Z large, you do a stationary phase approximation, and just from that, it tells you what combination of these two phases show up, and that's enough to tell you the coefficients of the Hankels. Okay, because you know for a fact that it has to be a linear combination of those guys. So here's the relation between the two solutions. The relation is that H nu 1 is J negative nu of Z minus e to the negative I nu pi J positive nu of Z over and if you haven't done these things in your life, I really encourage you to do them. It's extremely simple and nice, and you'll get a better feeling for what's going on when you use these limits in the future. All right. Okay, so now let's move on to calculating the wave function. So once again, remember that psi mod squared is e to the minus phi squared, and then I'm supposed to take the imaginary part, that was the capital A, which is this 1 over eta naught squared, and then it's the d eta log, and remember my solution had pulled out that overall negative eta to the 3/2. Sorry. So, which one of these things do we want? We want Hankel 2, okay? Because this was we want Hankel 2. So in other words, our solution, our F plus, is negative eta to the 3/2 Hankel 2 nu of minus k eta. And therefore, I have this d eta log, an imaginary part. The imaginary part's there. Hankel to negative k eta. Okay? So you see why this business is that we just talked about is going to be important, because what determined which solution we get is the behavior as eta goes to minus infinity, where the plane waves are the things that matter. So that picks out Hankel. On the other hand, we're now going to compute what all these things look like in the neighborhood of eta equals 0, where the things that behave nicely are Bessel. Okay, so okay, well, so let's just clean this up a little bit. This thing is real, so it's going to cancel out on the imaginary part. So this thing does not matter. And so in the end, I get just e to the minus phi squared. And in fact, let me make this look a little bit nicer. I'll put an eta naught cubed here, and then I'll have an eta naught, I'll have an eta dd eta of log Hankel 2 minus k eta, all at eta naught. Okay. So, now there are two obvious cases. Case 1 is when this parameter nu squared equals 9/4 minus m squared is positive. So this is when the particles are light compared to Hubble. Okay. Sorry? Yes, imaginary part. Thank you. Okay. So let's work it out. So what we need to do is expand Hankel in terms of Bessel. Did I erase it already? No, it's up there. Okay. So first, notice that this thing down here has an I in it, but it doesn't depend on eta. It's just a constant. Okay. So that's going to go away. So let's look at what. So we need to look at the eta dd eta of log of, now, this minus that, okay? So let me write it, j minus nu of z minus e to the I nu pi j plus nu of z. Now, what does this thing look like? This thing looks like, or k eta, sorry, minus k eta. So this thing looks like minus k eta to the nu plus dot dot dot, right? And this is fine. All the other terms here are subleading relative to this one, but everything here is going to be real, right? So I'm not going to get anything. To get something, I'm going to have to pick out this other guy, which has this I sine pi nu in it, right? So there's something here with a minus I sine nu pi minus k eta to the plus nu, again. So when I say plus dot dot dot, this is here. These are things that here that are analytic. There's just a power series from there. So it's also here the things that are analytic. So the imaginary part of eta dd eta log Hankel is, I'll suppress the I'll suppress these various nu dependence and constants and so on, is when I factor out this negative k eta to the nu, I'm left with 1 plus coefficient negative k eta to the 2 nu. Okay, so this is just negative, so that's a negative k eta to the 2 nu. I'm going to take the eta dd eta of it, I'm just going to pick out a factor negative k eta to the 2 nu. Equals some constant negative k eta to the 2 nu. So is that clear again? Let me write it schematically. There's something that looks like a negative k eta, actually really 1 negative k eta to the nu. Let me just write it a, and then I have plus ib negative k eta to the minus nu. So when I factor this out, it's 1 plus b over a to the sorry, there's a minus nu and plus nu. This is plus 2 nu. So when I take the log, of this thing, and I take the imaginary part of it, I just pick up there's a log of 1 plus this thing, and I just pick up negative k eta to the 2 nu. Okay? Proportional to negative k eta. All right, therefore, so we know the wave function. So psi mod squared equal to e to the minus phi squared over eta naught cubed times negative k eta naught to the 2 nu. Okay, or e to the minus phi squared k to the 2 nu, eta naught negative a naught to the over negative eta naught. 3 minus 2. All right, beautiful. So what is this back in position space? So it's very similar to the case of the conformally coupled scalar that we saw earlier, which here just corresponds to nu equals a half. So if I, for example, look at the 2-point function in space, I'll get phi of x, phi of y is equal to 1 over the physical distance, d of x and y, to the power of 3 minus 2 nu. Okay? So that's a beautifully scale, back of course, conformally invariant 2-point function. And this is the calculation that's identical in every way to the computation you do in ADS. Okay? So that's how we get scale invariant 2-point functions on the boundary. Yes? Yes. 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 Yeah. I'm just since, as I said, I'm trying to present things from a uniform point of view. We're just doing the path, and it will calculate the wave function, okay, and not go about. Of course, yeah. When we can translate everything, but for a variety of reasons, I prefer this point of view. Okay? And also, of course, it's equivalent to Schwinger-Keldysh. It's equivalent to we haven't done any of those things yet. But when we start doing interactions, we're computing the wave function, not the correlation function, so there'll be a few differences. But of course, they're all related. But I thought it would perhaps maybe also because you see all the other things in all the books, it might be fun to show. I mean, this is done in many places as well too, but it's just very slightly less standard. Okay, so let's now do the other case where the where we're going to see now I am in trouble, right? But just but I only have one more thing to do. Where the particles are heavy compared to Hubble. So now let's do the case where nu squared, where nu is 9/4 minus nu squared, 9/4 minus m squared, is negative. And so I'll set this equal to minus mu squared. Okay, then Hankel 2 now becomes, now that expansion that we talked about, just, I think, I think I erased it, unfortunately, but I think it's pretty obvious, is now looks like this. Okay. Okay, we're always doing the same computation now. Now, this thing is exponentially small when mu is big, so let's forget about this piece for now. Okay? Just for now, let's just ignore this guy, and let's just pick the first piece. If I just keep the first piece, h nu 2, again, if I take m log m eta dd eta log h2 this is just eta dd eta m log of this piece, which is minus k eta to the I mu. Okay, and well, that's just equal to mu. And hence, we get that psi of phi mod squared is equal to e to the minus phi squared mu over eta naught cubed and that's exactly the thing that we're talking about yesterday, the sort of intuitive thing. If I look at the 2-point function of this in space here, 5x, 5y, this is equal to 1 over mu, eta naught cubed over mu, delta cubed x minus y, which again is 1 over mu, the delta cubed of the actual distance vector between x and y, physical distance vector between x and y, okay? Is that clear? Just as in flat space, of course, as it should be. But this term is going to give us an interesting correction to it. Okay, so, so now include e to the minus mu pi piece. So now what do I have? Again, from the first term, I have what I had before, I mu, again, 1 plus dot, dot, dot. But I have minus e to the minus pi mu minus k eta to the minus I mu, 1 plus dot, dot, dot. And so m log of the above is mu, as we had before, mu, but then, sorry, m dd eta log of the above. But I have a correction, which is e to the minus pi mu, and something that oscillates. In fact, I get the real part of negative k eta to the minus 2I mu. I get both pieces, the positive and the negative frequency pieces. Eta naught. Okay, so what does this mean? This means that when we go back to position space, let's say, I look at the 2-point function, 5x, 5y, is the piece we had before, y delta cubed x minus y, the physical distance between x minus y, dx minus y. But we have a correction, which is minus e to the minus mu pi over the distance, the physical distance between x and y cubed times a cosine of m, again, physical distance, d x and y. Okay, so that's the oscillating piece that we were talking about before, and this is the physics of particle production. Now, I mean, that's what we said intuitively yesterday. You have a time-dependent background. It can produce everything there is, and so here we see it, right? You produce some particles. So there's a 2-point function that's oscillating. The particles are stable, so they're not going anywhere. So you have a 2-point function. Of course, there's a dilution by how far apart they were because they were produced nearby each other. They were stretched out a lot. But the phase remembers, even if they're very dilute, it remembers that they were there, and it tells you something about the time since they were created. Because they're just oscillating like e to the I mass times t the whole time they were created. Okay, now, let me make just a little obvious formal comment about this. This two-point function is not scale invariant, even with any imaginary scalings. Okay? Let's say I didn't have the cosine. Let's say I only had one of the exponents. Then I could say, then I might be able to say maybe the whole thing has, I might be able to say it goes like 1 over x minus y to the 3 halves plus I mu, or 1 over x minus y to the 3 halves minus, 1 over the distance to the 3 plus I mu, or 1 over the distance to the 3 minus I mu. Then they would have a scale symmetry with a funny imaginary dimension, but it would have a reasonable scale symmetry. But the actual two-point function for the actual real field we seem to care about does not. It forces you to take a linear combination of those two things, and it does not have a well-defined scale symmetry. So that's an important difference between DS and ADS. Everything, especially at this free level, everything is just analytic continuations of everything else. Everything is mathematically at that level trivial. But for these physical questions that we care about, as everyone knows who tries to say something about something like DSCFD, they say the words, you have to deal with operators with imaginary dimensions. Okay, that's exactly what we're seeing here. That imaginary dimensions for large dimension operators is simply the fact that massive particles oscillate. Okay, so and that's perfectly fine. There's nothing wrong with it. Of course, we can decompose these things into pieces that have well-defined behavior under dilations, but at least the obvious direct physical questions that we care about are not things that are directly scale invariant. So so this is one of the novelties. It's an obvious point, but it's something to keep in mind. A lot of the mathematics is identical. When you're talking about things that are light, it's extremely similar to what you do in ADS, but the novelty really starts happening when you have massive particles. You see them oscillate. This is the physics of time in a meaningful way, right? When the physics of time actually starts mattering, the rules start changing a little, the dictionary. I mean, again, the mathematics is essentially identical, but you're not supposed to be obviously looking at scale invariant object. You have to combine things with different scalings together to get physical observables and so on. So, okay, so I think we're done with the free part of the problem, and tomorrow we'll start talking about interaction.
So shouldn't that be 1 over mu times delta Q? Otherwise, these two dimensions.
Sorry?
Means in this expression.
Oh yes. I'm sorry. I'm sorry. Thank you very much. And in both of them as well. And I have no idea about that sign. So.
Yeah.
I think yesterday, actually, I wrote this formula wrong even at some point. As I was rushing, I put in over IR cutoff here. Of course, it's very important, the mass that goes in there as well. Is mu squared is m squared minus 9 quarter. I don't know. No, I think I'm sure this is all in I'll look by tomorrow. I think the introduction to a number of Juan's papers has these things in it. I'm pretty sure. So. But indeed, it's not in Borel and Davies. It does not quite do things like this. So
okay, there are no further questions. Let's disperse.